Now we are going to, okay, we have learned that we can have corrosion, potentially have corrosion, these layers, whatever, but what is the actual corrosion rate? What are the kinetics? And that's what we are going to learn in the next half an hour and in the next class. How can we interpret these corrosion rates and what do they mean and how you can get the best results out of these simulations. Okay, so regarding corrosion rates, I want to point out that when we are working with the corrosion analyzer, we will be working only in the AQ framework. So far, the isothermal calculations that we did were in the MSc. The pore bay diagrams were in the MSc. But every time that we work in the corrosion analyzer tool, we need to switch to the AQ framework. Is where we have developed most of our chemistry, developed most of our kinetics. And we are currently working on transitioning to the MSc. Again, because the MSc has more coverage in chemistry, it has a wider range of concentrations, a wider range of operations for temperatures and pressures. That's what most people are working on these days. We go to deeper wells, we go to more saline concentrations of these produced fluids. We start seeing critical fluids, supercritical fluids, changes in or having the production of acid phases, sulfuric acid, nitric acid, and all of that, right? So MSc is more relevant in all of those cases than the AQ. The AQ framework will limit you to an aqueous phase where you have dilute solutions, and it's where it works best, is what we have calibrated to date. Again, we're working on expanding our chemistry to use the MSc framework. These are some of the examples for the oil and gas industry, but again, we are expanding corrosion predictions to other industries such as metals and mining, water treatment, geothermal, carbon capture, etc. But at the end of the day, it's more or less the same idea, the same concepts, the same corrosion phenomena that people want to study. They want to study what is the effect of oxygen on the corrosion rate? What is the effect of CO2? What is the effect of H2S? What is the effect of pH? Do I need to add an acid? What happens to that acid? Is it going to increase, decrease? Well, it's going to decrease, for example, the scale formation, but how it will impact the chemistry of my water? Again, what happens if you have a flow in my system? How fast the fluid flows, and what is the effect on the corrosion rates? And of course, high temperatures and high pressures. All of these are very common in most of the industries. And I already showed you this slide of all the different applications that we do. But we're going to start with this simple example. And this simple example will teach us how to set up a corrosion rate, where to set up units, how to interpret results, etc. So the first example is a simple corrosion rate of carbon steel 1018 in an oxygenated sodium chloride solution. That's our first example. So we go back to the software, and in the software, we're going to save. I'm going to minimize these streams because they start becoming a little bit too much. And I'm going to add a stream, and we are going to rename it single point corrosion rate calculation. Why single point? Because it's going to be only one calculation. There are many other ways to understand corrosion rates. You can understand it using a survey or a dual survey, and we'll cover that. So we need the basics first. So you'll see that, again, for this version 11.5, the MSC framework is the default framework. And unfortunately, if we want to do corrosion rates, we need to make an extra click. We go to the AQ framework. Make sure that you have selected the AQ framework as the data bank for all the calculations. Okay, and then we can start. So let's say that for this example, we need to change the units. We haven't learned how to change units. So we go to the edit units, and there are different ways, but the fastest way is just to go here to the toolbar, and click on the units manager. That will open a new window. By default, the software always selects metrics, batch, moles. But we don't want metric batch moles. We want metric batch mass fraction. So we click on the moles option and select mass fraction. Okay, we selected mass fraction, but what is the meaning of that? What units were changed? So we go to the customize button here to see the specific units that were changed. So you'll see, because I changed my units to metric batch mass fraction, the stream amount is no longer moles, is mass, and is by default kilograms. The inflows, this change to mass fraction, that is mass percent or weight percent, right? And if you don't want mass or weight percent, you can always come here to the basis options and change mass percent to grams over gram, ppm mass. You have different options for the units. But we are happy with the mass fraction, the weight percent, so we leave it like that. These are the input, this is what we call the input variables. This is how we enter our data, right? So we're going to say we will have a kilogram of water and the composition of that water, like probably we will have sodium chloride, oxygen, etc. We also want to make sure that we have the right temperature and pressure units. So are we happy with degrees C and atmospheres? Okay. If you were working in a flowing system, then hours, days, seconds, you could change that. Other properties, you can also change the units. So for example, partial pressures become really, in some cases, very important. So you can change the units of that partial pressure down here, because it will not translate directly from the total pressure. You have to do it separately. Corrosion. Since it knows that we are in a corrosion calculation, it also offers the option to change the corrosion units. These corrosion units, for corrosion rates, you will have three options. You will have the millimeters per year, the micrometers per year, and the mils per year. Mils per year or MPYs, that's what it stands for. So by default, we will use millimeters per year. And I think that we haven't made very many changes here, so we are going to click OK to take the changes that we make, which are mostly the mass fraction units, and then we click OK one more time. So the next step is, now that we have changed the units, and you saw here that it's no longer moles, it's kilograms, it's 1 kilogram. And the inflow mass is in weight percent, mass percent. My solution is sodium chloride, and it's 3.5%. Usually that is what people use in the lab to represent seawater, and also oxygen. Oxygen, the the software doesn't include oxygenation conditions. So we need to account for the oxygen if this is a sample that is open to the air. So believe me that for now, we can do this calculation, but for now, believe me that 8 10 to the minus 4 is a saturated solution with oxygen in weight percent, 8 ppm. Okay, let's save. So this is an oxygenated chloride solution, and that's my bulk chemistry. Then we go to the next step, which is, okay, we define the chemistry. What's next? We just simply go and say, add a corrosion rate, right? So in here, you will see that two different, very similar to what happened to the pore bay, two different sections were added. First, calculation parameters. Calculation type, this is what we have learned before, isothermal calculation. So the software by default says, you know what, this is a temperature and pressure, constant temperature and pressure calculation, and we are going to assume that it's an isothermal. However, you have options. You can say that this is a bubble point, a dew point, a vapor fraction, all the other options that we had before in the single point, they are available here. Okay, so if you were to do a dew point calculation, corrosion calculation, you can do it directly here. Okay, so as an isothermal calculation, the flow type. The flow type, well, it's important to have fluid dynamics into account because they will have an impact on the mass transfer of reactive species. So is it static? Is it a pipe flow? Are you doing experiments in the laboratory where you have rotating disc electrodes, rotating cylinder electrodes? Are you going to assume this is a complete agitated solution so you don't have any diffusion problems? Things like that. So you can define any of these flow types in the software. For this example, we are going to leave it as static, as this flow type, the default. This is what I have been talking about. These are the scales that we have included in our studies for if the software knows in these inflows that you have CO2 and H2S in your system, it will include the effects of iron carbonate and iron sulfide on the corrosion rates. If you don't want them, you don't want them to be included in the calculation, you simply remove them. Okay, but keep in mind that that probably will increase your corrosion rate. This will be simulating something like maybe you know that you had a passive layer, but you had erosion or some type of removal of that layer, and then if you exclude it, that's what you will be simulating. Okay, but in general, we include these effects of those layers. Again, only when the system knows that you have CO2 and H2S in the inflows grid. Okay, the next step when setting this type of calculations is to define the contact surface. When we say contact surface, it's always the alloy, the metal, the elemental, the element. Okay, so by default, the software always uses a carbon steel. We have 29 different alloys in our data bank, and I already showed that list. Here is in an alphabetical order, but again, we have carbon steels, we have nickel alloys, we have aluminum alloys, we have copper nickel, stainless steels, and super 13 to 17 chromium stainless steels. What I have seen for not for geothermal, but for injection, for CO2 injection, lots of people are testing now the chromium, the chromium 13 stainless steel. And it's there, we have it there. If you want to go even fancier, you can select the Super 13 chrome, Super 15 chrome, Super 17 chrome. But you are the, Mariana and Joaquin, you are the expert, so you can just check which ones you need here. By default, we can just select carbon steel. Is our preferred one, what most people use. We can change here the name of this corrosion rate. We can name it carbon steel 1018. So we are aware of what's going on. What else? Another thing I want to notice, to point out once again, is that when you're doing corrosion, the software will also turn on the redox. I want you to notice that the redox is selected, okay? And it detects which is the element, the transition element that is part of the system, and turns it on. That is the iron in this case. And you see that I brought it here in the inflows. Okay. Down here to the right is a summary of everything that we have selected. For polarization curves, we also have the range of potentials, the number of points that are going to be calculated, the flow type, everything is summarized here to the right. And the button is green, so we can go ahead and calculate. Now, this calculation, you'll see that has more tabs than I have shown previously. It has a general corrosion tab. It has a localized corrosion tab, polarization curve tab, a report, and a depletion profile. Probably this one is empty because this is not a corrosion resistant alloy. Okay. But for the general corrosion rate, we can click here. And by default, the software always will show you, for this calculation, a corrosion rate as a function of temperature plot. But this is a single point calculation, so we don't need to see a plot. We need to see the data. So we click on View Data. And in here, it summarizes very few data, information here. Temperature, the corrosion rate, and the pH. The corrosion rate is 0.12, 0.13 millimeters per year. And maybe you can add, or you want to see other variables for corrosion values, for example, or you want some other additional stream parameters such as density or maybe the oxidation reduction potential. Anything that you need to add, you can simply add to this table. Okay, nothing out of the extraordinary that we haven't seen at the moment. The next tab is important. And it's probably not relevant for carbon steel, but if you were to have a stainless steel, it's more relevant. But it's okay. I can still use the carbon steel for this example to highlight what I want to say. And it's that the software will always plot in this localized corrosion tab, will always plot two potentials, the corrosion potential and the repassivation potential. The corrosion potential is this yellow circle here, yellow dot. So that's the driving force to corrosion, for the system to corrode. And there is another potential, which is the repassivation potential. And this repassivation potential is the driving force for the system, for the alloy, to repair itself. So if it got damaged, if it corroded, immediately repassivates, immediately forms another layer, and it protects itself. So one is the potential for self-destruction, and the other one is the potential for self-protection. Now, what the software does here is it compares these two values. It says, if my corrosion potential is higher than my repassivation potential, there will be a likelihood of localized corrosion to occur. Okay, and the software will also, let me just show the whole plot, will also show a third value that we call the maximum pit current density. And this maximum pit current density means that this is the current density of the pit that is being formed at the surface. Okay? So that means that these results here are showing me that this system, this water, oxygenated water in carbon steel, is pitting or is creating pits on my surface. You can see the data. Maybe it's easier to see what I'm talking about. This corrosion potential is higher than the repassivation potential. This is the maximum pit current density in amperes per square meter. There is a rule of thumb, not for carbon steel, but for stainless steels, that says that 1 ampere per square meter is usually equivalent to 1 millimeter per year in penetration depth. Okay, so you can always get an idea of what this value means regarding penetration depth of that pit. We also like to say that when we give this value for pit current densities, or this, we are saying that you will have a potential to have pits on your surface. Those could be also the initiation points for cracks. So you probably will also see in real life some cracking due to these initiators, these pit initiators, or induce these pits that can act as inducers for stress corrosion cracking. That is the localized corrosion. Any questions about that tab? Those results? Okay. It's all clear. Polarization curve. This polarization curve is what is giving us this corrosion rate. What does it mean? We just throw at you a bunch of lines and we say, yeah, that's the corrosion rate. No, it actually has a meaning. So what I'm going to do here is take the next 5 minutes to explain what do they mean. So I'm going to go to variables and I'm going to reduce the amount or clear all these half reactions. So as at the very beginning, when I was talking about the theory of corrosion, I talked about the half reactions and how the software includes all the anodic, meaning this reaction here, this is an anodic reaction, the dissolution of the metal. And it also includes the addition or the effect of cathodic reactions. So we have oxygen in the system, so we know that we have a reduction of oxygen on the metal surface. We also could have the reduction of hydrogen, and we do. We have the oxidation of oxygen, which is this one up here at the top. And I think maybe we will have the reduction of water. Let me see. Yeah, we do, of course. We have the reduction of water down here. Now, what the software does is it calculates at each potential, starts sending a line, right? And it adds up, for example, a minus 0.5 potential. It says we have to add the current contribution of this hydrogen line, of this water line, and this oxygen line. And that gives me a net current, a total current for the cathodic reactions. Same for higher potential. So if we go to 1 volt, the only contribution to the net current is this anodic reaction. So what we do is, or what the software does is it creates a plot. It's called a net current density. Again, it's the addition of all of those current contributions that we see in these different lines. That is my net current density, right? And where the net current density of the cathodic reactions is equal to the net current density of the anodic reactions is where we have our corrosion potential. Happens to be right here, where this oxygen line cuts the anodic line. Is where we have corrosion, cathodic and anodic and cathodic reactions. Anodic and cathodic currents are the same, and we have that corrosion potential. Now, this corrosion potential, okay, this corrosion potential here, this triangle, if you lower, let's say we're making a line here, the corresponding current value is what we call the corrosion current density. And this corrosion current density then is used, it's more or less 10 to the minus 1 amperes per square meter. And we use it, we back calculate that corrosion current density. We use the Faraday's law to calculate the corrosion rate, the general corrosion rate, this value. So basically Faraday's law, what it's doing is transferring electric terms, because we are talking about amperes, we are translating them into mass, or in this case, into penetration. So how much of the layer, or how much of your alloy you are losing per year based on this current density here, because we are using Faraday's law. Okay, so that's how the software calculates that corrosion rate. There is a final report which we are already familiar with. Is the report that summarizes all your inputs and all your outputs. Now you will see the calculated rates, corrosion rate, corrosion potential, maximum peak current density, etc. pH values of the solution, and everything that you are already familiar with. Okay, so that is all that, those are all the results that you get from a corrosion rate calculation from the software. Any questions about this? I forgot to show a plot, not a plot, but I like to show this here just to talk about the localized corrosion and the criterion that the software uses about the localized corrosion. So if the localized corrosion is higher than the repassivation, then localized corrosion is predicted. Okay. But that's it. That's all I had for today. And we managed to do at least one corrosion rate calculation. What we are going to cover next class is more corrosion rate calculations, how to set up set pH calculations, dew point calculations, maybe do either a custom calculation or an autoclave calculation. I know that there are Tenaris is using the software to do autoclave calculations. We will be covering that, and we will be also covering how to do surveys, corrosion rate surveys, how to basically study two different variables and the impact of those variables on the corrosion rates. And we will learn how to enter water analysis to do also corrosion rate calculations. Okay. So I will stop here if there are no any other questions. Mariana and Joaquin, what I would like is if you have any example regarding geothermal or autoclave or anything that is relevant for you, we can always do it in any of these rather than the custom calculation or the autoclave. We can just add it here and we can work in the class. The next class will be just doing a lot of calculations. and we can walk through your cases.
Maybe if we could do the same thing here as we do corrosion estimation, considering the presence of oxygen, but with a different steel that could be 13 chromium, for example. I wanted to see if we could see some difference related with pitting.
Oh yeah, but you want to do it now? We can just simply do this.
As you wish.
So we use the oxygenated solution here, right? I'm going to copy and paste. And you want to use 13 chrome? So we can just change here. 13 chrome is the first one. And that's it. So that's the other thing. You can always compare, right? The results. So we did carbon steel. We had a corrosion rate of 0.12, 0.13 for 13 chrome. With is 4.2, 4.3 10 to the minus 3 corrosion rate. For localized corrosion, we still see some pitting here. Corrosion value is higher than the repassivation value. Again, this is a 3.5 weight % sodium chloride solution. I don't know if those are the experiments that you are doing. It says that it has a propensity to localize corrosion. And for the polarization curve, we will need to analyze what are the main reactions that are going on in there.
What we have seen at the field, in this case is not a test, is that when we have oxygen with very low quantities of oxygen, we have localized corrosion.
And this is what is happening here. Okay, so in the next class, I actually have an example showing just that, but maybe I'll use this where you can actually do a sweep of oxygen concentration. And that sweep of oxygen concentration will give you the minimum oxygen concentration that you must have in the system, right? To avoid localized corrosion. So that is this example here for seawater. What is it?
Big rating.
Yeah, so I thought I had my, no, I don't. I thought I had a plot, but I don't. But it's okay, I have my example here. So it's the same idea, oxygen effect. So we have seawater, right? And we start playing, and this is what I was talking about, doing some surveys, where you start playing with the oxygen concentration. And as you increase the oxygen concentration, what happens to the localized corrosion, right? So you are below certain concentrations here, and then you reach a critical concentration where the corrosion potential goes above the repassivation potential, and the software is predicting localized corrosion. So I will teach you how to do that next class.
Thank you.
Thank you. Okay, so with this, I think it's the top of the hour. Thank you for your time. I know that these 3-hour classes are very long, but I try to do my best to give you breaks and be as relevant as possible. But yeah, I'll see you next class. And if you have any questions, I don't know. I think you have my email, right? Just want to make sure that you... Let me write it here. And if you have any questions regarding the training or the content that we have covered, then you can just simply send me an email. Okay, that's my email address. Okay, guys, so it was a pleasure to work with you, and I will be sending you the recording once it's rendered. Okay.